guys. I'm sure more people are going to start to arrive here shortly, but we'll get underway. Today we have a guest speaker for the Department of Geological Engineering, Tony Gilman. Tony Gilman is a geologist and geological engineer, experienced in geological mapping, structural geology, site characterization, rock mass classification, slope suitability analysis, and project management. Tony did his master's degree at Penn State in structural geology. He has over 15 years experience working in the environment, varying of mineral exploration, mining to geotechnical engineering. The focus of his work has mainly been on structural geology and rock mechanics. So the title of today's talk is Unmanned Aerial Vehicles and Geoscience and Engineering. Tony Gilman.
Thank you, Joe. So yeah, as Joe said, my name is Tony Gilman. I own a company called Terrane Aerial Mapping and Terrane Geoscience. My background is I went here for a geological engineering degree and did a master's degree in structural geology at Penn State University. And lately we've been working a lot. As Joe pointed out, my areas of expertise are structural geology and rock mechanics, and we've been working lately to combine drone data in those fields. So I'll just start out. I'm just going to show one of our multi-rotor drones. Go into a bit more detail about the equipment as we move forward, but this is just a photo of me flying a survey at a quarry site in Cape Breton, and just about to land one of the multi-rotors. So again, just to go over, Tony Gilman, that's myself. My business partner, Stefan Cruz, has a PhD in structural geology. He has been actually doing a sabbatical replacement here in the geology department this semester. And we've been, in addition to the rock mechanics, he's been looking at ways to use drone data analytics in structural geology. So just to give you a bit of an outline, I'll briefly go over just a review of photogrammetry, the equipment that we use to collect this data, the data collection itself, the survey accuracy, the positional accuracy, the camera resolution, etc. The data processing, so some of the data products that we can get out of these data, some of our analysis that we've done, and some examples of engineering and geoscience projects we've recently completed. So just the photogrammetry review. So photogrammetry is the science of making measurements from photographs, especially for discovering the exact position of surface points in X, Y, and Z. So as you can see from the image on the left here, we show two photos represented by the eyes at the top. And by knowing the position of each of these photos and having high overlap, we're allowed to pick matching points off of two sets of photos, and using trigonometry, calculate the northing, easting, and elevation of these points. So here's the equipment, one of the two drones that we commonly use, and one of the two main classes that are out there right now. This is a fixed wing UAV, comes with a high resolution camera and a built-in GPS. The second class that you're commonly seeing are multi-rotor UAVs. These have anywhere from 2 to 8 rotors. They have a built-in high resolution camera and GPS as well. So just to show you the data collection workflow, we start out with the UAV or the drone. We have our high resolution camera. We have a ground control station that's built into, that's a program that operates on a computer that talks with the drone while it's in the air. We take our aerial photographs. Each of these photographs has a built-in GPS location. We use photogrammetry processing software once we've landed these drones and downloaded the data to crunch it. Our first thing that we come up with is a point cloud. So we'll go into a bit more detail about the point clouds, but essentially you have a series of points. Each one of those points has a northing, easting, and elevation associated with it. And also, because we're doing this as an optical method, it has an RGB, a red, green, blue value associated with it. So some of the other products we can create from this, we can grid the data to come up with digital elevation, surface contours. We can do 3D model fly-throughs of the data, and ortho photos. So a typical survey block Well, this is why we sort of have the two different classes of drone, the fixed wing versus the multi-rotor. The fixed wing can stay in the air longer. It's essentially a glider, has a light battery. Some people are reporting up to 1 hour of flight time with these. So if you're getting an hour of flight time at 250 meters elevation, you can cover almost a square kilometer with one of these drones. Now, with the multi-rotor, we generally would fly lower, stays in the air less, so about 20 minutes, but we can get higher resolution data or map around things such as cliff faces, quarry walls, open pit mines, this sort of thing. And I'll show you some examples of that. So here's an example of collecting UAV data with a multi-rotor on a cliff face. So what we see here is each of these blue squares represents a photo location. And if you look close, you can actually see a black line on those blue squares. That black line is the vector or orientation in which that photo is taken. So each of these photos, remember, has a GPS location attached to it. So again, the data collection. This is a top-down view of a highway, and here we see two different photos with many overlapping points. So when we fly our UAV surveys, our photos generally overlap on the order of 80%. So the photogrammetry software can go through and pick out all these overlapping points and calculate its northing, easting, and elevation value. Here you're seeing photos on the order of 4 to 7 centimeters ground resolution. So you'll hear me talk about that a bit, and what that means is that JPEGs are made up of a series of pixels, as you may know, and each one of these pixels in the real world is a color that's 4 centimeters by 4 centimeters, making up the entire image. So here again, just an example of a quarry stockpile. High overlap allows the processing software to pick multiple matching points, as I just said. So the software goes through and it's going to see each individual tree, each individual little shadow. I think in this one there's a bulldozer. It'll pick up the corners of that, you name it. So survey accuracy. So this is one of the big questions and often concerns with UAVs or drones. There are three main issues. There's the positional location. So the northing, easting, and elevation. Where are we on Earth? Then there's also the photogrammetry matching software. So as I said, if you're comparing multiple photos and you're picking matching points, how accurate is that from photo to photo to photo? And what we find, and photogrammetry has been around for a very long time, what we find is that internally that's very consistent. So we're generally getting sub 10 centimeter, often way better, less than a centimeter precision with this photo matching. And the third is the resolution of the photos. So how far can we really zoom in and get a good look at these? But I'll mainly focus on, in the next few slides, the positional location. So where is it on Earth? Here we see, this is just a photo from a quarry site, but this is, if we're using the onboard UAV GPS. So as I said, every GPS has these built-in, or every UAV has these built-in GPSs. They generally have accuracies on the order of 1 meter. They're a lot the same, they're the same technology as our cell phone or a handheld Garmin GPS. So for some applications, this is enough. What that means is every one of these X, Y, and Z points in your point cloud will have a positional accuracy within 1 meter. But for a lot of applications, that's not enough. So what you see here is a differential GPS. So we will go out in the field, we'll lay out ground control points before surveying. When we lay out these ground control points, we survey them with a differential GPS that often has accuracies on the order of 3 centimeters. Here's an example of the ground control points we would lay out. So we put these out in the field. We try to distribute them evenly among the field area, both in X, Y, and Z, so in northing, easting, and elevation. We don't want them clustered in one corner, and we don't want them all at one elevation. We then go back and we survey them with a differential GPS. So that means we know where these are in the real world to 3 centimeter accuracy, approximately. Here you can see that previous stockpile image with, I've actually just superimposed this because it was hard to see it, but with one of the ground control points. So we will then have these ground control points throughout the area we're surveying, and they've been surveyed with the differential GPS. So going back to our workflow, when we get down to the fourth step here, photogrammetry processing, we can then feed these high accuracy ground control point locations into the final product. So what that does is it takes the entire image and shifts it appropriately and stretches it, whatever it has to do, and fits it to the high accuracy GPS points. So in a general survey, let's say something on the order of a ½ meter, we need 12 to 20 of these, depending on the changes in elevation and the type of topography we're dealing with. But what we find, once we have these 12 to 20 GPS points in there, and we feed the ground control points back into our model, is that our accuracies are very good throughout the entire model. This is a comparison of UAV with ground control points compared to ground-based LiDAR. You'll see these are volume estimates on a stockpile, similar to the stockpile I showed in the previous photo. And the percent difference here is on the order of 1.5 to 0.5%. So in those differences, it's hard to say which one is better. And really just the methodology that you use to get your volumes will give you those small differences. So I'll go into another example from repeatability of these type of surveys. This is the group of the UAV, the fixed wing UAV that I've shown that we fly is called Smart Planes, and they're out of Sweden. Smart Planes has done some repeat surveying of a mine site in Sweden, where they go back time and time again with fixed ground control points, and they fly this different times a year, different lighting conditions, and they get incredible repeatability. So northing, easting on the order of 0.8 centimeters from time to time to time, and elevation differences on the order of 1.3 centimeters. So the data processing. So the individual georeferenced photos that I talked about are stitched together with photogrammetry software. Now, this photogrammetry software, as I said, goes through and picks matching points on each of the images, and then based on knowing its location from one photo to another, can come up with our point cloud. So here we have a point cloud example of an open pit mine that we flew in Newfoundland. So this is a point cloud with 1.5 million points. This is an area on the order of 1/2 of a square kilometer, flown at probably 100 meters elevation, with a Ricoh high-resolution camera, with ground control points added as well. So with this survey, we did some independent testing, and we found that our coordinates, our X, Y, and Z point cloud data was on the order of sub 5 centimeters accuracy. Now, this being the first step, since we have a point cloud, which is very similar to LiDAR data, we can then grid that data and come up with a surface for it. So, well, okay, let me back up. First, once we stitch that together, we have an orthorectified georeferenced image, just a 2D image. But this being orthorectified means that if you were to go in here and measure the width of one of these roads in a drafting package, and then go out in the field and measure the width of one of those roads, it's to scale. Georeference, of course, just means it knows where it is in the real world. So here is a digital surface model. And this is what I was saying before. When you take your point cloud data, you grid that data, and you can fit a surface to it. Now, on this one, I'm also showing, from that surface, I've come up with topographic contours as well on this site. And in this one, interestingly, there were a few trucks down in the mine, Ford pickup trucks, and we were able to model those. And we could go in and measure the width of the box in the truck and come in centimeters of the size of the box of the truck. So here's an example of a digital terrain model. Now you just heard me talk of a digital surface model, and here's a digital terrain model. So the difference is, digital surface model is just a surface with everything you see in it. Trees, buildings, equipment, whatever it may be. Now in a digital terrain model, we use software to go through and actually remove things like trees, buildings, equipment, whatever it may be. So we can come up with what you would call a bare earth model. Here we're showing the 3D model. So this 3D model is the orthophoto that I showed you in the beginning, which again is orthorectified and georeferenced, draped over the digital surface model. So this, in our final software, we're allowed to spin these around and really get a good look at varying aspects of the mine. Now I'm just going to give you some examples of recent projects. So here's an example of using UAV data for geological mapping. Now, I'll back up and say that for applications like geological mapping and many field-based, we're never going to completely, nor should we, get away from field checking these. But what it can do is greatly reduce the time required in the field and increase the accuracy of these surveys. So here, as I say, is a geological mapping example. On the top, I'm showing the high-resolution orthophoto, and on the bottom, the final map. So we spent about an hour and a half at this outcrop, started to figure out what was going on, mapped in some of the main lithologies, did some descriptions, but then we're able to come back and we can really see the contacts when we zoom in. And of course, once we have these in ArcGIS or any GIS type package, you can zoom in much further and really get a good look at these. But even from this scale, you can see sort of the black on the left contact versus the whiter rocks on the right. And then you can see some of the offsets in the fault as well, based on that. So another example here, geological mapping. This is a mineral exploration property in northern Ontario. Now, originally we actually got into UAVs because we would find ourselves doing a lot of structural mapping and geology mapping on remote projects, and they would have just horrible base maps. At best, 5-meter resolution DEMs that are, SRTM type quality, or Google Earth, or whatever it may be. And for a lot of applications, when you get into detailed mapping, again, on the order of, as you can see here, this outcrop is about 100 meters in strike length. It's just not enough. So here we're able to go in, again, spend some time in the field, work out what's going on, but then come back and really accurately locate these lineaments, show offsets in our faults, map in mafic dikes in this case, and get a really good representation of what's going on geologically here. Again, this being, of course, only in 2D, and this has 3D applications as well. So here's an example just showing ore zones and fault zones in an open pit mine in 3D. So what you see here in red are the ore zones, or where the gold is, and what you see, the dashed black lines, are the faulting in this mine. So what you can't see is that I can now rotate this into 3D and project these faults at depth, which helps with planning of this mine. We can say stuff about the plunge of the ore deposits, visually get a good look at it. In addition to the excellent presentation you're able to get here with this. So here's an example. This is an oblique view of a highway road cut. So we're looking at this at sort of a low angle. But what you're seeing here is a plunging syncline. Now, this road cut is on the order of 200 meters long by 30 meters high. Up to where you could actually measure the plunge on this fold is, I don't know, it's on the order of 15 meters. There's no way to get up there. It wouldn't be safe. Plus, this outcrop is actually raveling in a lot of places with blocks, basketball-sized blocks. So it's just not safe to work under this outcrop for any amount of time. So we're able to go in, really map out the plunge of this, model it in 3D. You'll see here on the left, we can show a fault. So, some of the applications here, the geometry of these faults can be worked out really well in 3D. This could have applications in a mineral exploration environment. For instance, if your gold mineralization, say, was controlled by the plunge of your synclines. But we can also work out the size of these blocks and any stability issues related to rock mechanics, which if you're in an open pit mine, a quarry, or a highway cut, can have very valuable applications as well. So I'll just show you another example. This is actually the same highway cut. Down in this zone is the syncline we were talking about, and this whole highway cut is an anticline-syncline pair that does something like this. Now, this highway cut, as I said before, is around 200 meters long. It is 30 meters high, and they were having a problem with blocks falling off the top, bouncing off these benches, and making their way to the road. Not something you want. So we went in and we were able to map this entire road cut in 3D using our multi-rotor UAV, and then come away and spend some time in the field, of course, characterizing the joints and coming up with some of the geotechnical characteristics of the faults. And then we used software from the French Geological Survey called QFacets. This is an open source software, and what QFacets allows us to do is go in and actually pick out these joint orientations. So we now not only have just a pretty picture, we have joint orientations that we can put on a stereo net for rock mechanics analysis. And I'll just show you the next slide. Here we've removed the background noise, which was a lot of the blue. And you'll see our yellows and our light blues to grays here. The light grays, which I'll show in the next slide, is bedding. And our yellows are one of the main dominant joint sets. One interesting thing about this outcrop is you'll see this really big patch of yellow in this region. And I'll focus in on this a bit more, but there's a potentially unstable block right here. And this is about 20 meters up. There's no way to get up there. It was really hard to get a look at it from down on the road. And we were really able to characterize that discontinuity using this method, whereas before we could not have. So here, just focusing in on just the bedding data. And of course, if I go back, we can do this for any one of the different orientations of discontinuity sets. With this work, I should also thank Joseph Cormier, who introduced me, because Joe's done a lot as part of his an independent study here, working with these data and really figuring out some of the open source software, and it's been very valuable. Here's an example zoomed in on some of that software, just showing each of these patches has a strike and dip associated with it. So this is just showing the different joint sets that you're able to characterize automatically with these methods. So here's some comparison between our geotechnical mapping using the UAV and also using just traditional field mapping. So on the left you see the UAV mapping, and on the right you see field mapping. The first thing you should notice is that they agree quite well. So that's obviously the first thing we want for a QA/QC check. The second is we get actually a tighter cluster with the UAV mapping. And that's just a function of we probably have on the order of 500 points for bedding on the UAV, and we maybe have 20 from our field mapping on the right. So arguably the UAV is actually quite a bit more accurate in characterizing the orientation here. And just another example using what we've called joint set 1. This was this dominant yellow one that I tried to show previously. And again, we're able to characterize these in close agreement, and we believe that the UAV mapping is actually doing a better job. So here's another example of geotechnical mapping. It's along the same lines. But this was actually an open pit mine. We were working on the design of an open pit mine in Ontario, and adjacent to it was a previous open pit mine. Now, it would be really nice to get in there and get some geotechnical data, but this particular mine was owned by Goldcorp, and they've had some stability issues of these walls. No people were allowed to go in this. We were not getting down there to take a single strike and dip. So we were able to fly this over. This is a top-down view, and then fly the cliff face as well, and come up with our strike and dip of these discontinuities remotely. And what this did is there was no outcrop in this region. We had oriented core data for our discontinuities, and then the potential of using this site. So it allowed us to take our oriented core data and come up with, to bolster our oriented core data, so to QA/QC check it. And this method worked very well in this location. Just back to, this is the block that I highlighted on that highway cut. From the roadway, it was really difficult. This, again, is up in the air on the order of 20 meters. It was really difficult to get a look at this and to characterize the orientation of these joints. But this is making a free block that could potentially be susceptible to sliding. And this is quite large. This is, a lot more than basketball size. This is on the order of probably the size of this desk here. So if this falls in the road, it's quite dangerous. Now I'll just skip. Here's looking at that close-up of the orientation of those joints and that block. The block, it's a little different view, but the block is right in here. And what we're able to do is really get a look to measure the size of that block, to measure the discontinuities that define it in 3D, and then we can do a kinematic stability analysis on it. Now, previously we have tried to do these types of stability analysis, but you really would sort of be doing it by using your thumb and getting a best estimate. Here, we're able to use real numbers and really come up with what's going on. And what we found is, from just standing down on the road, there was a lot of parallax on this. And this bedding plane in this region right here was not really that steep. So the risk in fact, it was less steep than the angle of friction, so the risk of this actually sliding was found to be quite low. So what we've decided to do is just to monitor it for a while, and which brings us to another really great application of UAVs. Because of the cost of flying these types of things, we can go back next year, refly the same zone, and compare the point clouds year over year. So we can do change detection on these. So huge applications for landslides, coastal erosion, any of these types of applications. And what we do is we bring this into software. We use one called Cloud Compare, and we bring one point cloud in, and then the next one, and it'll actually show us contours of what has changed in that time. Now obviously we're restricted using UAVs to the accuracy. So you need movements above 5 centimeters before you start to see something realistically, before we have confidence in saying that. So this is just another view. Again, I just talked about change detection, but that's that same block in another view. And this is showing the point cloud. And what we'll do next year is go in, survey this again, and compare the two to see what's happening. So I'm now just going to talk about a few other applications that we've been quite heavily involved in since getting into the drone market. The first one would be volumes for stockpiles. I mean, this was the first one everyone picked up on. It's just a great tool for it. Previous to this, you've had surveyors out there with a GPS and a pole walking on these stockpiles. Depending on the time of year, it's unsafe. The accuracy or the number of points that you're going to get is quite low. At best, a surveyor is going to take a point every square meter. We get on the order of 200 points per square meter. So here just showing a 3D rendition of one of these stockpiles. So what we're able to do is we can go in, clip out one of these stockpiles using software. We end up with a 3D model of just the stockpile. We then use software to fit a base to this. There's numerous methods to do this. Hopefully it's flat and easy and you can just put a basal one elevation, but oftentimes if it changes in one orientation or the other, you have to do an interpretation. But then we simply, we can just create a volume or come up with calculate a volume. This is just an example showing a stockpile yard with the various volumes that we're able to pick out. So previously in a lot of these cases, you know, a surveyor may have been, depending on how big the yard is, anywhere from 2 to 6 days to do some of these sites. We usually can go in and fly the biggest quarries in 2 hours. Crunch the data in 36 hours and have people report in 72 hours. So the time difference is really huge. Just another example, here we're showing some stockpiles with the contours overlaid on it. And this is an example for a safety point of view. These are salt stockpiles in Pugwash, Nova Scotia. Because it's salt, they put black tarps over this because they don't want the rain to wash it away. These black tarps are slippery, and then you get them covered in snow, and it's just a disaster. And they were for years just walking these. Or in some cases, they were just using a measuring tape and coming up with a very simple geometry. So we're able to improve their volumes greatly. Another example, life of quarry studies. Because we get such a good 3D DEM on something, this site is on the order of 2 square kilometers. The area in red shows their property boundary of the quarry, i.e. where they're allowed to take rock from. And the little black highlighted areas show the benches of rock that still remain. So we'll go in there. You'll notice there's trees on some of these. We use software to remove the trees to come up with a digital terrain model of these. We then have an upper surface, and we just use a basal quarry elevation. I think it's in the next slide. We then just put in a basal quarry elevation, and we can come up with a volume of those benches. So this can give them reserve estimates, or year over year we can even do this and compare how much they're taking out. But in addition to that, we can also use these comparisons year over year for looking at stability of these quarry walls, which sort of goes back to some of my examples of the highway as well. So the next, I believe, we're getting close to the end. This is just a fly-through video that we're able to do. It's usually not this chunky. We're really able to animate these So you can see some equipment down in the mine in this case. And this is done on a bit lower resolution, so I can show it here. But, and you know, these more than anything, people use them in safety videos. We've had some interest from mining companies for promotional type stuff, but it's really just to show the ability of some of this cloud data. So in summary, I think UAVs offer improved data quality in many cases. The best example I think I presented today being the highway road cut, and safer field data collection. Those two are kind of combined there because realistically on that highway road cut, we just would not have been able to get stuff above sort of a meter height. And again, it wasn't safe to be working under there because there was a lot of rock fall. Also, because of the UAV technology and the cost keeps coming down, we can take lower costs over traditional survey techniques. So in a lot of cases, it's overkill to have a ground-based LiDAR on a small rock slope like that. It's just, yeah, it's beautiful data, but it's just not necessary. It's too much money. So. And I'll leave you with one of the other, probably the best applications, the drones. So that concludes my talk, and if there's any questions, I'd be happy to take them.
Questions for Tony?
I had a question.
Yeah.
So as far as the GPS receiver technology on the UAVs, just curious, there's been some technology and there's some emerging technologies that allow you to actually perform kinematic positioning directed to the drone.
Yeah.
So you have absolute positions of a centimeter at the drone level. What we're finding is that it decreases the level of ground control and thus the time of the field crews even further.
Yeah.
Is that something that you guys take into consideration or thinking about?
We're aware of that. It's just becomes an economic question at this point. But I mean, the SenseFly UAV has really good GNSS locations coming from it right now. And the drone that we showed, our multi-rotor, is from a company out of Halifax called Sky Squirrel, and they've been working already on having differential GPS on those. So I would say within a few years we will have that and it will be standard. Yeah. So because right now, as you say, laying out the ground control points often, well, no, I wouldn't say often, always takes us longer than actually flying the surveys. So, good. Thank you. Yeah.
Has anybody ever used this for like river research? So for could you get this imagery of a river using a camera, consider like the turbidity of the water, which is pretty clear. Could you build a ETM for like substrate?
I've actually there have been some papers out there on that. I can't speak to it with authority, but there have been some people that have looked into that. I do know that some of our surveys that have been flown over, like in estuaries and places with very tranquil water, we, just from processing our data in a normal sense, we get bathymetry of that. Now, how accurate it is, I do not have a clue, but I do know some people have been working on that. So, but any current at all and water, photogrammetry does a horrible job with water, any spikes or waves, and it's, you know, it thinks one point is 100 meters in the air and it thinks the next one is down 50 meters. And so water is tricky, but in tranquil water, we have seen some degree of elevation model. So.
Anyone?
Yeah.
For rock slope monitoring, how many times have you been back to one particular site?
There's a couple sites in quarries that we've done only twice at this point. Yeah. So that we're still building a database of those.
So are you getting some idea of what, learn levels or what has to happen or do you just really report on one model?
Yeah, so at this point, I mean, we just don't have a big enough data set to report on numerous ones, but I mean, you do see those differences readily. Let's say a basketball-sized block has fallen. It'll highlight when you compare the two clouds. You will see that basketball-sized block missing if it's fallen since the first survey. So, but as I said, you still are left with your accuracies within there, which 5-10 centimeters at best. So if you're looking, we had someone who was interested in, they were working on a very deep quarry, I'm not sure where, but they were interested in potential rock burst problems, and they wanted to know sort of sub-centimeter movements by flying these things time and time again. It's just not the right tool for that. So again, it has to be in the right environment. I see large landslides, something that you're looking for, movement in a particular area. Again, big blocks on slopes, that sort of thing. That's being the sweet spot here. Yeah.
And do you think if it's possible to monitor any sort of vibration with drones? Let's say you have a chimney that is 200 meters long and it's vibrating, you have a drone looking at it.
Yeah, I don't think I can answer that. That's not something I've really thought that much about. Yeah, I don't know if you maybe could do something with video with that. I'm not sure. But now, if the chimney had heat, you might do something with thermal imaging there. But anything that's moving too fast, in my experience, photogrammetry doesn't like either. So, yeah, go ahead.
The things that you've been doing with the multi-rotor drone, what elevation have you been flying at? And secondly, if you flew lower, do you think you could get higher accuracy?
Well, to answer your first question, we generally don't fly that much higher than 100 meters. And currently we're not super happy with the camera. We'd like to get a higher resolution camera on that. So that becomes, it's sort of that off play between what's the resolution of your camera versus your height. And so we end up flying lower often with that to get higher resolution photos. But whether we're getting better positional accuracy, I don't think I can say we are necessarily getting better positional accuracy. Although I suppose depending on contrast and resolution photos and how many points it's picking, we may be.
So what would be the lowest you typically fly?
Well, I mean, if we're the highway road cut jobs we do, which are vertical faces, we fly those at 12 meters away from them. So we get incredible detail. I think that image, if we could